In this video, I'll try to answer student questions from lessons 4.1 through 7 in the Organic Chemistry 2 Primer 2018. The first question is from lesson 4.1, asking how two pi bonds can be orthogonal and asking about whether this would mean that the hydrogens on the left side are vertical and the hydrogens on the right side are in and out of the plane. And I think this question is asking about a particular graphic on page 9 of your lecture guide. And the reason that the p orbitals that make the pi bond have to be orthogonal to one another when the same carbon tries to make two pi bonds, one in each direction, is that once I use, say, the px orbital on this central atom here, I only have the pz and the py p orbitals left to make another pi bond. So those orbitals that make the bond are 90 degrees apart from one another, and I've shown one set of orbitals in blue and the other in red to emphasize that fact. So that's why the two pi bonds have to be orthogonal to one another. And the second part of the question, they said, well, would that mean that these h's on the left would be straight up and down, and the h's on the right would be one towards us, one away from us? And that is true, and that's what's shown in the picture here. The second question, also from lesson 4.1, is asking, well, why is this alkene with a heat of hydrogenation of minus 28 more stable than this alkene with a heat of hydrogenation of minus 54.1, even though this one is pi conjugated? If I show this pictorial, you'd say, okay, if I have this alkene and it only has to give off 28.6 kcal per mole to get to pentane, whereas this one has to give off 54.1, this one will be higher in energy. And the thing that's missing from comparing these two to one another is that this one over here is pi conjugate, but you're doing a hydrogenation on two pi bonds. So if we look at the table that was on page 10, these are the two that the student asked about, right? 54.1, 28.6. The thing is that this one has a pi bond right here, just like this one does. So you'd expect minus 28.6 for just this bond if there was no special stability from being pi conjugate. But this molecule that's pi conjugate also has this pi bond, which looks like this one. It's at the end of the molecule. So it should also have the heat of hydrogenation for that one. Took those together, that's 58.7. So it would give off more heat. It would be less stable than the one that gives off 54.1. So you see, the fact that this pi conjugated molecule only gives off 54.1, but you'd predict 58.7, that actually tells you that you have 4.6 kcals of extra stability per mole. You can actually quantify how much more stable the pi conjugated one is by being pi conjugated, rather than having this isolated pi bond and this isolated pi bond not pi conjugated with anything else. The next question comes from lesson 4.3. A couple people asked this question, and it's asking, well, what is an electron withdrawing group? How do you recognize one? And this is in reference to the fact that electron withdrawing groups on a dienophile will speed up a Diels-Alder reaction. So of course it's going to be important to recognize what is an electron withdrawing group in order to figure out whether a Diels-Alder reaction could be sped up by it. And we're going to learn a lot more about how to identify electron donating or electron withdrawing groups in future lessons, but for now, electron withdrawing really just refers to some group that pulls electrons towards it. And electrons are negative, so anything that is partial positive would have the influence of pulling electrons towards it in that molecule. And the reason this speeds up a Diels-Alder reaction is if I start to pull electrons a little bit that way, then these electrons will be pulled towards that site, and that'll help you get that Diels-Alder reaction started. Now, partial positive charge on that atom, what are some specific examples? Well, a good one is a carbonyl, and we've seen a couple examples like this in specific Diels-Alder problems we've done. So there's a partial plus there. Another one that I've used in some practice problems is this one. There's a partial plus there. So really, for this point in the class, you're just looking for, is the atom attached to my dienophile a partially positively charged atom? This next question also has to do with the Diels-Alder reaction, lesson 4.3. And it says, well, on one of the tutorial website, one of the PDF files that you have there. It mentions these endo and exo products, and do you need to know those? And if you didn't take a look at that tutorial website, the link is given here, but it's also listed in the module. So this question of endo versus exo has to do with cases where your Diels Alder reaction produces these types of bicyclic structures. And in those cases, you have a choice between pointing your electron withdrawing substituent up, which is the opposite direction that this double bond is. That's referred to as the exo product, or it's pointing down and the double bonded unit is leaning down. But this endo product is going to be favored for all the cases you're going to see in this class, and the reason for this becomes evident if we consider the partial charges. So if I draw out this electron withdrawing substituent, there's a partial positive on this carbon. And if you remember that these sp2 hybridized carbons are a little more electronegative than the sp3 hybridized carbons to which they're attached, there's a partial minus here. So one of the reasons that the endo product is favored is that in the transition state, while you're pushing these two pieces together, the partial plus will start to be attracted towards where you're going to be making this double bond. So the endo product is going to be favored, and you'll draw that when you are trying to draw the major products for these reactions in this class. Here's a question from lesson 4.4. This is the lesson talking about aromaticity and how one determines whether a molecule is aromatic or not. And specifically, this is asking and saying, well, one of the criteria for aromaticity is that the molecule must be planar, but how are we supposed to know if a molecule is planar or not? And is any molecule greater than 6 atoms around non-planar? So these large ring sizes that are flexible confuse a lot of people. A lot of people had this question. And to address this, I want to back up and talk about cycloalkane, something we learned about way back in Organic 1. And we probably all know that the cyclopropane, cyclobutane have a lot of ring strain. And they stay planar even though there is a lot of ring strain. And the reason for that is they're not flexible enough to bend in order to become more stable to relieve that ring strain. All right, so small ring sizes we've seen before are pretty rigid. Once we start to get to ring sizes of 5 or 6, the ring size of 5 can bend a little bit, but by the time we get to a ring size of 6, this can undergo distortion so that instead of being a flat hexagon like this, one of the tips bends up and one of the tips bends down, and by doing so, you alleviate a lot of the rings. So all these cases of cycloalkanes in the planar form have ring strain. Only when they're flexible enough, though, can they bend and distort to avoid some of that instability. The same is going to be true for these aromatic compounds. So if we evaluate whether these are aromatic or anti-aromatic, we always start off by assuming that the molecule is going to be planar. All right, so you don't have to know ahead of time going into a problem whether they're planar or not. You make an assumption they're planar, then you check and see whether they will be. Now, again, in the case of these small rings, we would figure out these have 4 electrons. That's an anti-aromatic number, any multiple of 4. You'd say, okay, they would like to twist in some way to avoid being unstable. Remember, the anti-aromatic is less stable than non-aromatic. But these will stay planar even though they're anti-aromatic because they're rigid. The same reason that the cycloalkanes couldn't twist even though there was ring strain. Once you get to a bigger ring size, though, well, now it's flexible. So if you have ring strain, a ring size of 6 or greater will bend quite a bit to avoid that ring strain. This example, if it stays planar, it's going to be anti-aromatic. Remember, it has to be planar to be anti-aromatic. But it's a 7-membered ring, so it's big enough to be able to bend maybe into a shape like this so that it won't be anti-aromatic, it'll be non-aromatic. Right, and by doing so, that's more stable than being anti-aromatic. So the molecules only bend if they get more stable by doing so. I want to address the second part of the question, though. Is any molecule greater than 6 atoms around non-planar? No, there are some that are planar. For example, if we take the cycloheptatriene, same general scaffold we had here, but we change the charge to a plus charge instead of a minus charge. Now, instead of having 8 electrons, 2, 4, 6, 8, that's anti-aromatic. This one has 6 electrons, and that's aromatic. So it's aromatic if it's planar, which is super stable if it's planar. So there's nothing to cause it to twist. So it can be planar if it's greater than 6 atoms around, if by being planar it stays stable. But once you get to that bigger ring size that's flexible, if it's going to be unstable if it stays planar, of course it's going to twist and bend just like the cyclohexane did to bend into the chair to avoid the ring strain. The next question is also about the aromaticity lesson 4.4. What is this N in the Huckel rule? And we know we need 4N plus 2 electrons in the pi system. Really what this is saying is that to be anti-aromatic, if a ring system has some multiple of 4 electrons in that pi system, it's going to be anti-aromatic. So the N can be any integer. So any multiple of 4 around a planar ring will cause the molecule to have diminished stability because of how the electrons are lined up in the different molecular orbitals. To be aromatic, adding 2 more electrons to multiple of 4 causes an increase in stability. At that point you filled all the proper orbitals for maximizing the stability, without going to drawing all the molecular orbitals for you. So the N can be any integer. Now, for all intents and purposes, 4N means really if you have 4 electrons or 8 electrons, we're not going to get up to molecules with 12 electrons very often. So 4 and 8 are what you'll usually see for anti-aromatic in this course. And that means that 2, 6, and 10, really we usually see 2 and 6 if we're not talking about bigger molecules for aromatic. So you don't really have to use too many values of N. So N is usually 0, 1, or 2 for the purpose of small kind of molecules we see in our class. Now really a confusing question for a lot of people in many, many years of organic chemistry is this question from lesson 4.5 about how can you tell the relative basicity of nitrogen atoms. And I guess I went over this in class a little bit on Tuesday, but we have to first consider what kind of reaction we're talking about if we're thinking about the basicity of a nitrogen. Well, if the nitrogen is going to be a base, it's got to react with an acid to make a salt, right? This is what we learned for our definition of bases in general chemistry. So say I add hydrochloric acid. Well, hydrochloric acid is a strong acid. It dissociates into H plus and Cl minus in solution. It's all general chemistry, maybe even high school chemistry stuff. And if the nitrogen is the base, the nitrogen is going to pull that proton out of the solution so that the solution is less acidic after that. And we get this salt. So the key feature that I focused on for our class is we need to pull that lone pair away from the nitrogen if this nitrogen is going to act as a base. So let's maybe try to categorize the types of lone pairs we see in these different organic molecules. Well, a lone pair might be providing a lot of stability to the starting material before the acid-base reaction by making the molecule aromatic. All right. Remember that aromaticity is a really stabilizing force, so this lone pair that is needed for that might be hard to take away. Even before we learned about aromaticity, back in Organic 1, we learned about resonance. And if I can spread out that lone pair, I can have a little bit of resonance stabilization with that lone pair. It doesn't make this molecule aromatic. You see, we don't have resonance all the way around the ring, but it's still giving some stability to the molecule compared to something without resonance. Then at the bottom, I give 2 cases of lone pairs that are not involved in resonance, and one of them is on sp2 hybridized nitrogen, and one is on sp3 hybridized nitrogen. So with that in mind, we have to remember that acidity and basicity are thermodynamic properties. Remember that the acidity can be defined by the pKa, which is a negative log of the Ka, an equilibrium constant. So we're really trying to think about an equilibrium or a thermodynamic property. So we can figure this out just by looking at stabilities. Specifically, the more favorable the acid-base reaction, the stronger the base. So let's consider the stability of the starting materials. Well, if something has aromaticity, like what I've called AR on the previous page, you see these little abbreviations, I'm going to use those here. The thing that has aromaticity is going to have the most stable molecule, right? Something with resonance has the next most stable stability, and these lone pairs on sp3 or sp2 hybridized nitrogens that are nice neutral compounds, but no resonance or aromaticity, I'll say they're about the same stability. Now, after we do the acid-base reaction, this is what we're trying to figure out. How favorable is that reaction? Let's say that I take my nice aromatic molecule I'm calling AR, and I take this lone pair away. Well, this thing is not aromatic anymore. So it's not nearly as stable as something that had aromaticity. So you've lost this much stability. And if I characterize what the product is, it's something that's not aromatic, and it's got the plus charge on this sp3 hybridized nitrogen. All right, so that's the first case. Well, what happens if we try to make this resonance stabilized species act as a base? We'll do the acid-base reaction. It starts off looking like this over here. Take the lone pair and give it to this proton. So we have the species on the right. Well, just like when the aromatic molecule reacted, I've put a plus charge on sp3 hybridized nitrogen, and there's no resonance anymore. So the type of product you have is about the same whether you start with the aromatic one or the resonance stabilized one. It should have similar stability. I haven't lost quite as much stability with the resonance one, so I'd expect that reaction to be a little bit easier. Now if I take this particular molecule that isn't stabilized by resonance or aromaticity, it goes with this sp3 right here, that's this molecule. Well, it's less stable than the resonance stabilized or aromatic to start with, but after I do the acid-base reaction, I just put the proton on the nitrogen. It's still an sp3 hybridized nitrogen, and all three of those products, whether they derive from the aromatic one, the resonance stabilized one, or the sp3 hybridized nitrogen that wasn't in resonance or aromaticity, the products all are not aromatic, plus charge on sp3 hybridized nitrogen. And you'll see I only lose a little bit of stability when I do that. So that's the most favorable reaction so far. Now the trickiest part for most students comes when you consider the difference between the sp2 hybridized and the sp3 hybridized, because neither of those has resonance or aromaticity. And I'm showing the product, which is this, as being less stable when the positive charge is on an sp2 hybridized nitrogen as compared to all the other cases where the plus charge ended up on an sp3 hybridized nitrogen. This is because an sp2 hybridized nitrogen is more electronegative than is an sp3 hybridized nitrogen. And you'd rather have a negative charge on something that's more electronegative. But I'm trying to force a positive charge to go on it. So that's going to be less stable. So the basicity is going to mirror these trends. The strongest base is the one where you have the most likely reaction, the one where you've lost the least stability. Alright, so the sp3 is going to be the strongest base of all of these. The next would be the sp2. The next would be the resonance stabilized one. And the weakest base will be the one that was aromatic, and then you went and took all that aromatic stability away from it. And now we're going to switch gears, and we have a question here from lesson 7.1 through 2. And this question a few other people had as well, but it asks what causes a longer pi conjugated chain to have a lower energy transition in the UV-Vis spectrum. All right, so we kind of just stated that as a general rule, didn't explain it in great detail. The primer says something about greater stability after you've excited. So let's think about this in a little more detail. Well, let's think about the process that happens. If we're trying to think about stability and energy involved for a process, we need to think about where the electrons are. Now, all the electrons are in bonds when you have just some kind of pi conjugated or molecule with pi bonds. All right, so 2 electrons are in a pi bond here, let's say. When this molecule interacts with the light, you have only 1 electron in the bond, and one of them has gone to some anti-bonding orbital. All right, so that's the key thing. The key thing is that after excitation, one of the pi bonds has only 1 electron in it, which we can think of as a radical. It's a little bit more complicated than that. There are things called polarons and solitons and bipolarons that are formed, but we think of all these different species like radicals. So if we think about that in sort of a simplified way, using radicals that we're familiar with from our organic chemistry studies, we can think about a molecule that does not have pi conjugation and a molecule that does have pi conjugation. And remember, we're trying to figure out how much energy is going to be necessary to cause the change, the excitation, from the ground state to this excited state. So if we make a radical, take one of the 2 electrons out of this bond and put it, say, here, we have a radical that's not resonance stabilized. If we take 1 electron out of, let's say, this pi bond right here and put it, say, here, well, you have a resonance stabilized radical. This is going to be a heck of a lot more stable than this not resonance stabilized, also secondary radical. So it's just going to take you less energy to form this more stabilized species. And that's why you have a lower energy transition for the longer pi conjugated chains.